So welcome to another live session for the online astronomy courses, our last before the holiday season. We'll probably get one more in early to mid-December. The floor is open for your questions.
All right, our first question today comes from an online viewer, a live viewer from Rami, who asks, how do you think the interstellar asteroid, I think it's pronounced Oumuamua, got its prolonged shape, or its pronounced shape, and is it possible to send space probes on to such interstellar objects?
So the asteroid you're referring to has been in the news recently. It's a near-Earth visitor, a fairly small asteroid, Oumuamua. So it's a Hawaiian name because it was found and tracked at the Hawaiian observatories looking at nearby Earth-crossing objects, NEOs as they're called. And it's striking because it's highly elongated. It's basically almost the shape of a needle. So it's a space rock that is 10 times longer than it is wide. And that's very unusual. Basically, in astronomy, gravity tends to make almost everything symmetric or circular because it pulls in every direction. So moons and planets are round, extremely round. And you have to go down to the size of objects, small moons like Mars moons, Phobos and Deimos, which are sort of potato-shaped, or the asteroids themselves, which are often elongated. Sometimes asteroids can be dumbbell-shaped because it's quite often for asteroids to be hybrid objects, which is to say, in the collisions that occur in the asteroid belt, two pieces stuck together or were held together by gravity without actually binding as rock and melting together. And so there are sort of dumbbell-shaped asteroids, but this sort of needle-shaped asteroid is extremely unusual. And basically, nobody exactly knows what it is. There's a possibility that it is also a hybrid object, a string of rocks held together by gravity and weak intermolecular forces, but that's pretty unstable and fragile, so it's unlikely it could survive. And if you have a collision between large rocks, it's really unusual or unlikely to shatter off or spin off a piece that's this elongated. So for the moment, it remains a bit of a geological mystery as one of the most elongated objects known in deep space. As for visiting it or capturing it or sending a probe to it, it's not on a very amenable orbit. There are things that come closer to the Earth, and there are also things that come closer to the Earth with smaller relative velocities. So the relative velocity of this object, as close as it does come to the Earth, made it extremely difficult to intercept. So that's really not on anyone's radar.
All right, the follow-up question is, do you think it would attract space dirt or dust on its travels?
It will, as would any asteroid. But remember that interstellar space and the regions of the solar system, even in the depth, even in the middle of the asteroid belt, they're actually very sparsely populated. There are, of course, many smaller rocks and grains of sand and dust grain-sized objects than there are big rocks. But, interstellar space and the space between planets is still an almost perfect vacuum. So an object like this will just pick up very tiny amounts of extra particles. And again, the gravity of it is weak because it's a small object, so it's not going to pull in matter from a large distance. So basically, no, it's a pretty pristine object, and it's going to stay pretty much the way it is for a long time.
Right, the next question is from Edwin, who is on with us live, who asked, can you talk about the differences between space-based telescopes and potential moon and Mars-based telescopes and the pros and cons of each of those?
Sure. The big difference between space and ground-based telescopes historically has been that going in each direction. On the direction of space-based telescopes being more challenging, a space-based telescope per square meter of collecting surface, whatever wavelength it works at, is 10, 20, maybe even 30 times more expensive than a ground-based telescope. So the act of launching a telescope and the limited number of launch vehicles for large mirrors and the robustness and testing that a space telescope has to go through to make it survive launch, which is a very violent procedure, makes space telescopes very expensive. So all NASA space telescopes have been over $1 billion. The Hubble Space Telescope, if you count all the refurbishment missions, is probably $10 or $11 billion and counting. And even at the time of launch, it was $2 or $3 billion. The James Webb Space Telescope was originally budgeted at a couple of billion and is now over $8 billion. So these are extreme, but space telescopes are always expensive. Now, for $1 billion on the ground, you can get one of the next generation super large telescopes like the GMT we're building in Chile, or the 30-meter telescope that California observatories want to put on Mauna Kea. So you can get a 20 or 30-meter telescope. And JWST, of course, is 6.5 meters, which is several times less light gathering power. So you have to have a good reason to go into space since it's so expensive and difficult. And that reason historically was twofold. It was the sharpness of the images you could make when you're above the Earth's atmosphere, and it was the fact that other regions of the electromagnetic spectrum are open to you. Remember, from the surface of the ground under the atmosphere with a lot of absorbing gases and water vapor, only the visible window, a small region of the infrared, the near infrared, and the radio regime, longer wavelengths than a few millimeters or a millimeter, are available. Everything else is blocked. All the ultraviolet, all the X-ray, all the gamma ray, and most of the infrared. Now, one of those two reasons has essentially gone away. Adaptive optics on the ground, which is essentially a standard part of the toolkit of a big ground-based telescope, is able to correct for the turbulent motions in the Earth's atmosphere. And so essentially render images diffraction limited according to the size of your mirror. And we're doing that in Arizona, and all major observatories now do adaptive optics. So the sharpest picture ever made of deep space was actually taken at our Magellan telescope in Chile a couple of years ago, which is to say an image sharper than any by the Hubble Space Telescope. So that advantage of space is essentially being completely eroded by adaptive optics. And then when you have larger light gathering power for visible imaging, you would probably want to do ground-based work. Space, however, still retains its unique niche for regions of the electromagnetic spectrum where the radiation can't reach us. So let me take the second part of the question, sort of treat it as a separate question. Why would we go beyond the Earth or beyond near Earth orbit to put telescopes on other bodies like the Moon or Mars? So remember, the ground-based telescopes and the Earth-based orbiting telescopes are quite close. The Earth-based telescopes in orbit are like half a day's drive straight up, so low Earth orbit, not too far away. To go to the Moon or Mars, let's just say the Moon, you have to have a very compelling reason, because that's a difficult journey and it increases the cost enormously. The Moon has been on people's radar for a space-based observatory for decades, actually. NASA did design studies of a Moon observatory back in the 70s and 80s. And there's no showstopper in doing it, it's just very expensive. The cost of doing it has now reduced because of robotics, because of 3D printing, because of technologies that would accelerate the construction of an observatory without humans being involved, and humans are always the expensive part of the equation. So the cost of doing a lunar observatory has actually gone down. But what are the reasons for doing it? Well, the reasons are that the dark side of the Moon is a wonderful place to do astronomy. It's exceptionally dark, of course, if you get beyond a place, if you're shielded from sunlight and you're shielded from Earth shine or reflected light from the Earth, it's fantastically dark. It's also very stable because, of course, the Moon is not geologically active. So it's a perfectly still geological environment. And there's no atmosphere on the Moon, of course, so it's as good as deep space for that. And of course, once you're on the Moon, you could set up infrastructure and perhaps robotically build quite a large facility, including interferometers, where you have many telescopes working together in a way that would be very difficult to do on the Earth. So interest has revived as the idea of a Moon base starts to come into view. Interest has revived in a lunar observatory. There's no particular reason to go to Mars for an observatory because Mars has an atmosphere. It's a lot further away and more expensive. So if you're going to go away from the Earth for telescopes of any kind, radio astronomers would be as excited by this as optical astronomers, then the Moon is a pretty exciting place.
All right, our next question is from a live viewer who asks, I want to know if we have any realistic idea of what's inside a black hole, and what is a white hole?
So the best answer to what's inside a black hole is all of the stuff that made it as it grew from a seed. That's a fairly good guess. Since things can fall in but can't come out, then if you were able to keep an inventory of what were the ingredients of the black hole. In fact, what passed through the event horizon as the collapsed star core got to the point where the gravity was so intense that nothing could escape, then that's what's inside a black hole. And for most stellar mass black holes, which are large, the cores of large stars at the end of their life, what's inside the black hole is just gas, normal material containing hydrogen and helium in cosmic proportions with smaller amounts of heavy elements, compressed to an incredible degree, compressed by factors of trillions compared to normal matter on Earth. So that's what a black hole contains, just normal material. The interesting thing about a black hole, of course, because the black hole is opaque and the black hole gives you no hint as to what made it or the path by which it came to exist, two identical black holes, identical mass and identical in appearance, could have been made in completely different ways and in essentially from completely different things. And there's no way we'd know just by looking at them. So black holes are sort of mute to their actual ingredients, but we know how black holes are created, and so we have a pretty good guess as to what the material that's inside them is. White holes are a hypothetical construct out of relativity. There's no evidence they exist, and in most versions of relativity where white holes are invoked, they represent a place where space-time is not smooth, the way that we think the universe is mostly smooth and almost Euclidean in its shape of space-time. If space-time gets convoluted or contorted, then it's obviously possible for space-time to collapse on itself or connect, to be multiply connected, such as a black hole point corresponds to an exit point in another region of space-time. So you can do this in general relativity. The theory of gravity that leads to the prediction of black holes also leads to the possibility of white holes, but there's no evidence they exist. And actually, it's more than that. We don't even really know of regions of the universe where the conditions would be suitable for the existence of a white hole.
All right, our next question is from Bill, who's on with us live, who asks, what is the structure that holds a globular cluster together?
The globular clusters are the oldest stellar systems that sort of form the bony extended skeleton of a galaxy like the Milky Way or an elliptical galaxy. So it's the old star component of a galaxy. And in the formation theory of galaxies collapse from clouds of gas and dust, often early in the universe, first few billion years. The first part of the Milky Way formation was probably a couple of billion years after the Big Bang. And in that early collapse phase, there's sub-collapse of clouds, so it's not one single cloud collapsing uniformly. There's a lot of condensing on different scales. And some of those scales lead to the formation of regions where hundreds of thousands or even millions of stars will form in a roughly spherical region. And that's essentially what a globular cluster is. It's a set of hundreds of thousands up to a few million stars that have formed by collapse at the same time, all at the same time, and typically early in the history of a galaxy. And they form a spherical shape where all the stars are in elliptical orbits around each other. Centrally concentrated, so there's more mass in the center and less on the outside. And each of the globular clusters in the Milky Way and in the other galaxies we study occupy the halo of the galaxy, which is a spherical or nearly spherical outer extent of the galaxy, or otherwise there's very low density of stars. There are some individual halo stars, single stars in this region of space too, but the most impressive and massive sets of stars are the globular clusters. Globular clusters are also hypothesized to occasionally contain massive black holes, which is to say more massive than an individual star, but less massive than the black holes at the center of galaxies. So there's tantalizing evidence that the biggest globular clusters have black holes of a few thousand up to maybe a few tens of thousands of times the mass of the sun that have formed in their dense cores. And that's the only place in the universe where we know of black holes that mass. But like I said, this evidence is not compelling yet. It's just suggestive. Globular clusters are also the sets of stars we use to age date galaxies because we think they formed in the first collapse phase of the biggest clouds of gas and dust that make galaxies. And so by age dating the stars in the globular clusters, which are often the oldest stars we know of in the universe, you get a very good bound on the age of a galaxy.
All right, the next question is from Grigoris, who is on with us live, who asks, hello, Professor. I was wondering what advice you would give to a biologist who wants to enter the field of astrobiology.
So astrobiology is a very exciting and growing subject. Astronomy, perhaps as a whole, is growing. I've viewed the sort of job statistics in physical sciences. And while physics is growing very mildly, if at all, in terms of professional opportunities, astronomy is growing at a reasonable clip, maybe a few percent a year in terms of job openings in research institutes or academia. I would say astrobiology, which is a small subfield, is growing at an even faster rate. And that's driven, of course, by the excitement of the interdisciplinary research and by the enormous boom in exoplanets, where not only are there thousands of exoplanets known, but we're also homing in on Earth-like habitable planets where we're actually starting to face the question of what biology might be on all these Earth-like planets that Kepler and other facilities are finding. So it's a good time to be an astrobiologist. The other part of the research that's very active is, of course, the research based on the extremes of life on Earth, how Earth life formed, either by inspection, looking for the oldest forms of life, or by lab or even theoretical experiments, how it might have happened, and also looking at the full limits of life on Earth, extremophiles, microbes that occupy extreme niches of physical conditions that sort of test the boundaries of what we understand biology to be. So there are all of these kind of studies open to an astrobiologist. It's still a tricky business to get a career going in because interdisciplinary work is still not as well supported as it should be. The research agencies like National Science Foundation lag behind in funding astrobiology. NASA has some astrobiology funding, but it's about $50 million a year. And remember, that's out of an $18 billion NASA budget, so not really very much. There's some private or foundation money going into astrobiology, but also not much. So while it's an exciting and growing field, the job opportunities which exist in universities, that we hire in astrobiology every now and then, it's one of the growing fields for us here in Arizona, and nationally are definitely there, but it's still a small field. And it's rewards people who are willing to be kind of brave and bridge disciplines. I would say the conventional biology departments in major universities are still somewhat skeptical of astrobiology. They think terrestrial biology is plenty rich enough to be studied, and they don't necessarily need to go into a field where there's no evidence, because there is no evidence of life beyond Earth. So most astrobiologists are actually employed in astronomy or planetary science programs rather than in the biology departments.
All right, our next question is from Angelo, who's on with us live, who asks, I would like to know how stellar nucleosynthesis works. Does it depend on star mass, volume, etc.?
Sure. Stellar nucleosynthesis, which is the formation of heavy elements or all elements in the universe, is the story of every star and why it shines. So all the stars you see, the 6,000 stars you can see on the dark side in the night sky, and then, of course, the 100 billion stars or more in the Milky Way, if you could see all of them, are all shining by fusion, by stellar nucleosynthesis. For most of those stars, including the sun, it's the very first stage of nucleosynthesis where you go from the lightest element, hydrogen, to the next heaviest stable element, helium, in 3 steps in the proton-proton chain. That's what the sun's doing, and that's what stars like the sun are doing. So most heavy element production or nucleosynthesis occurs for low mass elements. The sun will make a little bit of carbon before it dies, but that's about all. To get the heavier elements, and to answer the question, nucleosynthesis really does depend on mass. If you can say what the star's mass is as it begins its life, an astronomer, an astrophysicist could predict quite confidently which heavy elements it will make during its life or at the end of its life, and pretty much how much of those heavy elements. That's a fairly reliable calculation. As the mass of a star increases, the ability to fuse heavier and heavier elements increases, because what must be done is the gravity and the compression must lead to a temperature where nuclear repulsion can be overcome. As the atomic number goes up, the electrical repulsive force goes up, and so a higher temperature is required to make fusion occur. In the sun, that temperature is above 10 million Kelvin, and the central temperature is 15 million. And so in the central quarter of the sun's core, hydrogen is being turned into helium. But the sun, late in its life, will compress enough for other nuclear fuels to be ignited. To get the heaviest elements, however, requires stars much more massive than the sun, 5, 10, 15, 20 times more massive than the sun. In those stars, some of the heavy elements are made in a crescendo late in the star's life. As each nuclear fuel is exhausted, the star readjusts, reequilibrates, collapses, reaches a new higher temperature, and a new nuclear fuel is ignited. And so you move up the periodic table. Iron is the end point of this as the most stable element, the most stable nucleus. And so to go beyond that requires extra energy. And that extra energy in a very massive star comes from the detonation in a supernova. So the supernova blast wave can also make heavy elements. That's the R process for rapid. The S process for slow is a more gentle version of this, where in the envelope of a giant star, neutrons can be injected into atomic nuclei because they have no electrical force, so there's no resistance to them joining a nucleus. And then inverse beta decay causes the atomic number to rise by 1. So we've essentially moved out the periodic table that way. And the third pathway to make heavy elements is something that's fairly new on the table as a result of discovery just a few months ago, the discovery of the neutron star collision that led to one of the signals for the Gravitational Wave Observatory LIGO. The neutron star collision allowed models of neutron star mergers to be tested, and it turns out that in a neutron star collision, the blast wave of relativistic neutrons that's sent off enriches the material around it, the interstellar medium, and creates an enormous amount of heavy elements. So heavy elements are also created by neutron star mergers. All of these things are going on all the time in all the galaxies in the universe, and so over time, steadily, the fraction of heavy elements in the universe is going up.
All right, our next question is from a live viewer. Daniel asks, in your opinion, do you believe that life, even if unicellular, exists somewhere in our solar system? If so, where do you think would be the best place to start looking first?
So microbial life in our solar system, it's a big question. It's possible we may find life by diagnosing the atmosphere of an Earth-like planet in another solar system. And that could happen in the next 5 to 7 years, given experiments that are being planned. But the solar system probably has 10, 12, maybe even 15 locations, mostly moons in the outer solar system, where all the three basic ingredients for life are present, which is to say carbon-rich material, liquid water, and a local source of energy. So even far from the sun, under an icy, rocky crust, on moons of the giant planets, the ingredients for life can exist. So with a dozen or so habitable spots in the solar system, what are the most likely to have actually created microbes, if any? It's, of course, possible that the creation of microbes, even given the right raw materials and the right physical conditions, is a difficult or slow process. We don't actually know how long it took on the Earth. It may have taken a few 100 million years, and a few 100 million years is, a long time, so it's possible that it might take much longer under slightly different conditions or never happen at all. As for the best or most likely spot, if you had to place a bet, essentially, and go to one place, subsurface Mars is still a reasonable place because it's one of the closest objects to get to. But liquid water on Mars is likely to be fairly far down. And if it exists at all in aquifers, they're most likely to be 30, 50, maybe 100 meters under the surface. And we don't have any technology on any rover, current or planned, that will drill that far down. Therefore, the next best place is probably the place that we know to have liquid oceans all the way around, which is Europa, moon of Jupiter. There's a Europa Clipper mission, which is being planned for the late part of the next decade. And there's vigorous debate as to whether that mission should be made more ambitious and aggressive and actually have a lander and have some way of diagnosing what's going on under the ice. There's a mission concept from the 1970s that's certainly technically feasible, to land a nuclear power plant on the European surface and use the nuclear reactor to melt slowly through the ice and release a hydrobot to look for life in the European Ocean. And in a sense, I would pick Europa as the favorite target because we know there's an enormous body of water under that ice, and exploring that body of water would be fascinating. Of course, at the small end, there's Enceladus, which we know has the subsurface liquid water, which produces the icy jets and geysers. That's a small moon, only, much smaller moon than most of the moons in the solar system. And then for a wild bet on life, Titan is the best because Titan has also liquid oceans, but the liquid is ethane, methane, ammonia, and a little bit of water at a very cold temperature under a nitrogen atmosphere. Nobody really knows whether biology is possible with that kind of geochemistry. There's also rather modest amounts of free energy there. There's some subsurface heating from cryovolcanism, but this would be a very frigid form of life, and so metabolically it would probably operate differently from terrestrial life. So I'd put my best bet on Europa, followed by suitable drilling technology on Mars to get to one of those aquifers.
All right, our next question from a live viewer, Zakaria asks, can we go to an exoplanet in the future?
Very difficult and slow. So Breakthrough Starshot, a project announced about a year and a half ago, is planning to go to Proxima Centauri system on the off chance, maybe the significant probability that there's an exo-Earth in that nearby star system. There's actually two shots because there are two stars that are potentially going to have habitable planets around them. Well, that's sort of 4 and a bit light years away. And so with nanobot technology accelerated by solar sails, powered by very high powered lasers, that's the Breakthrough Starshot concept, you could potentially accelerate these tiny probes, probably a gram in mass, up to fractions of the speed of light, 5, maybe 10%, let's say 5%. And at that point, it's a century, close to a century, to get to the Proxima Centauri system, assuming you can decelerate when you get there by using the solar sail in reverse. And then drop the nanobots down through the atmosphere of an Earth-like planet, where they have very small sensors and maybe even small cameras. Camera technology is miniaturizing to the point where you can actually put a camera on a 1 gram micro probe. So that's an actual planned project, which has some funding, $100 million, not enough to do it, of course, but that's just seed funding. And that will get us our remote sensing capability with robotic messengers to a nearby star in less than a century. And that's about as good as it gets, because the next nearest Earth, or most of the Earth-like planets we're finding, are 10 or 20, 30, 40 light years away. So 3, 5, 10 times further away, and therefore longer to get to. For humans or large objects, we're talking about 1 gram nanobots as opposed to 60 or 70 kilo humans inside a spacecraft. The energy requirements are just simply insane to do that in any kind of reasonable time. We have no plausible way of accelerating a spacecraft like the kind that got the Apollo astronauts to the moon to anything like even a few % of the speed of light. So those journeys would have to be made by human voyagers willing to be put on ice or essentially cryonically frozen for journeys that would probably last millennia. And that's obviously very far off, almost science fictional.
All right, the next question is from Rajarshi, who is on with us live, who asks, at a quantum level, do Einstein's general and special theories of relativity fail?
Yes and no. The special theory of relativity is really mute to quantum theory. It's the only element of special relativity that involves a micro scale is the description of light itself, light as an electromagnetic wave. And that doesn't violate any ideas of quantum theory. So special relativity and quantum theory do not conflict, but in part that's because special relativity does not push quantum theory in any direct way. It works in a sort of classical realm where quantum theory is known to behave well and describe nature quite reasonably. For general relativity, the situation is definitely different because In most situations, large situations of space-time, stars, galaxies, the kind of the expansion of the universe itself, which general relativity is applied to, quantum effects also don't matter because you're dealing with macroscopic, very large-scale physics. But in the places where general relativity and the micro world meet, then there are problems that arise. One of those places is, of course, the early universe, the Big Bang theory. So at the origin of the Big Bang, tracing time backwards, there's obviously a time at which, for the whole universe, the sort of space-time that would eventually unfold to contain 100 billion galaxies and all their stars in a vast universe, there's a point at which you have to have quantum theory in the mix. And we have no such unified theory to unite general relativity and quantum theory. That's the theory that Einstein was looking for the last 15 years of his life, and he failed, and others have failed since, although there's active work on it. So at the Big Bang, where you do need these theories to be reconciled, there is no reconciliation. The other place where there's no reconciliation and some problems is in terms of black holes. So black holes are obviously situations of extreme gravity, but some of the properties of black holes can only be understood by invoking quantum theory. The classic example of that is Hawking radiation. So Stephen Hawking in the 1970s speculated, theoretically, and it's been pretty much consistent with observation, that black holes do not just have a mass and a spin, those were the two properties they were assumed to have originally, but they also have a temperature, and they have an amount of entropy or disorder, so they have a thermodynamic property. And that temperature implies that black holes radiate. Now, the temperature of a black hole, the mass of the sun, is a tiny, tiny fraction of a Kelvin. It's a fantastically small temperature, almost close to absolute zero, but it's a real temperature in the theory. And by the corollary of having that temperature and the black hole radiating, since mass and energy are equivalent, is that black holes are evaporating. So that phenomenon is called Hawking radiation, predicted in the mid-1970s. And it involves a situation where quantum theory and gravity theory have to play together. But there are all sorts of problems now in the research arena with Hawking radiation, not with the prediction of Hawking radiation, which hasn't been tested, but with the fact that when you try and do proper quantum analysis of a black hole event horizon, you end up predicting things like firewalls, because you have to deal with this sort of information paradox, the fact that information is apparently lost in a black hole. And entropy is, of course, one way of describing a number of states of information. So this ignorance or knowledge of this information state of a black hole inside the event horizon creates a real problem in quantum theory. And really, there's a whole research field sprung up around this. There are whole conferences given over to it. Some of the smartest people in gravity theory and quantum theory are working on it. And there's some pretty big arguments still on the table that are unresolved. And people are excited by that in a sense because they think that's how progress will be made.
All right. The next question, sort of related, is what happens with information in a black hole?
So it's a matter of some debate and no large-scale agreement amongst physicists and astrophysicists. Anything that, if you recall the classical definition of entropy from Boltzmann's time, or related entropy to the logarithm of the number of equivalent microscopic states. So a large entropy is just a situation where there's a large number of equivalent microscopic states that can't be distinguished from each other. Black holes actually have very large amount of entropy. And if you want a sort of colloquial way to think of it, you can just think of the fact that no matter what you made up, what you threw together in space to make a black hole, it's the same black hole. It just has mass, spin, and a radiation temperature, according to Hawking. So you could make a black hole in millions of different ways from millions of different initial configurations or ingredients that went into the black hole, and they all end up looking the same. And the reverse argument of that, the corollary of that, is black holes have a very large amount of entropy. And they also, therefore, have a large amount of embedded information, which is the information of what made them up. And once you've just sitting there with a black hole, you seem to have lost that information. And anything that falls in, the trivial example often given is you drop an encyclopedia into a black hole, passes the event horizon, that information is lost from the rest of the universe forever, as far as we know. And this has been called the information paradox. And so it's a problem because the question is, why is it a problem? That's just what black holes do. The reason it's a problem is because in quantum theory, states are supposed to be reversible. So if you have particle interactions at a fundamental level, you're supposed to be able to play the time arrow backwards and get information uniquely and reversibly out of a quantum state. In other words, a quantum or particle interaction can proceed backwards or forwards in time equally well. And so that information shouldn't be lost. And yet in a black hole, the microscopic information at the quantum level does seem to be lost. And that's the heart of the information paradox. And it simply hasn't been resolved. There's a very active debate in the research community about how to resolve the information paradox. But for the moment, we're stuck with it.
Okay, the next question is from Marcos, who is on with us live, who asks, can you please explain the phenomena observed to infer the existence of dark energy?
Yes, it's important to remember that as long as dark energy's been with us, which is to say 22 years now since it was first imputed or discovered in 1995, it's still primarily based on a single type of observation. And that observation is the acceleration of the cosmic expansion. And that observation is based on finding particular objects that astronomers call standard candles. It's a very archaic term, but it really, just think of it as a standard light bulb. That is an astronomical object whose luminosity or intrinsic brightness is very well understood and very well calibrated. And the kind of object that was used for the dark energy discovery was type 1a supernovae. So these are supernovae that go off in binary star systems where matter is spooned onto the companion star at such a well-regulated and steady rate that when it explodes essentially the same way every time, with a luminosity or a brightness or an energy that's always within 10% of every other example of a supernova. So when you observe the brightness of these supernovae, these standard candles or standard light bulbs, at different distances or redshifts in the universe, you can compare near and far and make inferences about how the universe has been expanding. So as people look back in time and out in space, they compare the brightness of the supernovae, these exploding stars, at large distances and look-back times, and short distances and small look-back times. What they anticipated, given that the universe contained mass, was that the universe, as you look back in time, has been decelerating. And so they expected to see faster expansion in the past that's been slowing down since then, the braking effect of dark matter. They saw actually the opposite. As they looked out in space, they saw that the universe has actually been accelerating and was moving slower then. And the way that gets measured is that the supernovae they observed were about 20 or 30% fainter than they expected. The explanation being that the universe has been expanding faster and faster, and so stretching out the distance and therefore making those supernovae fainter at a large distance. It's a pretty good argument if you trust the supernovae as indicators of distance. And so several research groups worked hard to check each other using different objects, getting the same result. And in the mid-1990s, and certainly by 1998, 99, it was clear that the observation was correct. If these supernovae were indeed standard light bulbs, the universe is accelerating now from what it was a few billion years ago. And the question is, what could possibly cause an accelerating expansion? And the answer people came up with was dark energy. So it's important to know that dark energy, the observation is of an accelerating expansion, and that's a pretty good and confirmed observation that nobody disputes anymore. The inference as to what causes it is the thing we call dark energy. And still, after 22 years, nobody understands what dark energy is. There's no fundamental physical explanation for it. There's no identification of an agent or an entity or a particle or field or anything you can imagine in physics that could cause the accelerating expansion. And so astronomers are left with a very big puzzle.
Okay, our next question is from John, who's on with us live. We have a couple of related questions. The first one is, can you comment on the significance of the recent kilonova explosion?
So this was the merger of neutron stars. LIGO, the Laser Interferometric Gravitational Observatory, the twin detectors in Washington State and Louisiana State, measuring gravitational waves, had found a couple of gravitational wave events that were merging black holes, and those were very well publicized and, of course, led to the award of a Nobel Prize just a few months ago to three of the founder members of that collaboration. And then an event came along, which was, of course, first discovered months ago, but it takes a while for them to be totally sure of it and release the information to the rest of the world, which did not seem to fit the black hole merger hypothesis. By the energy of the gravitational wave and the nature of the gravitational wave form, it was clear that these were lower mass objects, and it was clear that they were neutron stars. The good news, that may be a little disappointing if you're like black holes, that they're only neutron stars, less massive, less dense stellar remnants. But the exciting news for the rest of astronomy is that when neutron stars merge, when black holes merge, essentially you see nothing except one bigger black hole resulting and gravity waves coming off. When neutron stars merge, you see a combined neutron star actually becomes a black hole, gravity waves coming off. You also see a lot of electromagnetic phenomena, because neutron stars, when they merge, accelerate neutrons into a blast wave that carries enormous energy into the surrounding medium. And that energy plowing into the surrounding medium is what creates the kilonova, which is, you know, a sort of colloquial way of saying 1,000 times more than a standard supernova. It also accelerates the neutrons to the point where they can create heavy elements in the surrounding gas. And in some of the models, this kilonova event, this neutron star merger, created hundreds of Earth masses of gold, platinum, and silver, sort of precious elements, in really less than a minute, in seconds. An amazing outcome. Because of all this energy that's deposited, the neutron star merger was able to be observed across the electromagnetic spectrum. So the gravitational wave detection was the trigger for a set of ground-based and space-based observatories following up the neutron star merger. I think at the end, 70 or 80 different observatories were involved in this work. Some of them saw the blast wave at optical and infrared wavelengths. Others in space, very excitingly, saw a gamma ray burst, thereby proving that at least some of the gamma ray bursts, phenomenon that's been known since the 1960s, are associated with neutron star mergers. And this was a feast. This was a field day and a feast for astronomy. And the little tagline or phrase that's emerged from this is multi-messenger astronomy, where the messengers of information in the universe are now not just electromagnetic radiation, but gravitational waves as well. So 70 observatories, thousands of astronomers involved, hundreds of papers have been written, and this is just one event. So I think LIGO, in addition to finding merging black holes, is going to fuel a lot of other astronomy studies.
Right, our next question, which is related, is from Erhard, who asks, am I correct in saying gravitational waves have basically confirmed the expansion rate of the universe as previously calculated? And what is next for gravitational waves?
Yes, that's an interesting question, because it's a little side light on the detection of gravity waves. So when you know what kind of the logic is this: when you detect a gravitational wave signature, that the signature itself, the shape of the chirp, it's called a chirp because you could turn the frequency into a sound and sonify it, as has been done on the web for these events. The chirp, or the particular waveform of the coalescence, completely defines the masses of the two objects that merged. And so you know what the masses of the objects were. The theory of gravity tells you how strong the gravitational waves that should come out of that merger, and you've measured the strength of the signal with your detector. The other thing you know, this distinguishes gravity waves from electromagnetic waves. Electromagnetic waves decline in their measured strength with the square of the distance from the source. And that's because you don't actually measure the amplitude of an electromagnetic wave, you measure the intensity, and the intensity is the amplitude squared. So light and all the other forms of electromagnetic radiation diminish in strength by the square of the distance to the source. With gravity waves, you are actually measuring the amplitude, so it goes down as a single power, linearly with distance. That's actually good news for gravity waves, because it means they get weaker at a much slower rate than electromagnetic waves do, moving out in the universe, which in turn gives the gravity wave observatories enormous reach through the universe. So you have all these pieces of information. You know the mass of things that merged. you know what the theory says about the strength of that signal, and then by the strength of the signal you observe, you can calculate their distance. And so, yes, the gravity wave signatures have allowed us to measure the distance very directly to this small number of astrophysical sources, and so corroborate our different estimates for the expansion rate of the universe. And the cross-check is very good. So our other estimates of expansion rate from other methods seem to be correct.
All right, the next question is from Jaffe, who asks, hi, do you think we can find the place the Big Bang occurred by finding a kind of center of our universe, and what will be left there? A giant black hole, maybe?
It seems like there should be a center. I mean, if, everything seems to have a place. The Earth is a place, the sun is a place, the center of our galaxy is a place. But when it comes to the universe itself, there appears to be no center. So the first inkling of this comes from the expansion itself. What we see is all galaxies moving away from us, with a couple of exceptions. Andromeda is being pulled towards us by mutual gravity. But on large scales, galaxies move away from us. And the further away they are, the faster they move away from us. That's the Hubble expansion. But the Hubble expansion is such that if we lived on another galaxy, we'd see exactly the same thing. So every galaxy observes all of the galaxies moving away from it with the Hubble expansion. And so logically, either one galaxy is the center, or they all are, or none are. And the answer to the question is none are, because there's no way to distinguish a center from the expansion itself, the nature of the expansion. The other aspect of this is the microwave background radiation. So we see this radiation, first detected in 1964, left over from the Big Bang and cooled by a 1,000-fold expansion of the universe since about 400,000 years after the Big Bang, when that radiation was released as red waves of light, essentially. Since then, it's been stretched out by the expansion. And the fact that we see that radiation all around us with essentially equal intensity in every direction, to 1 part in 10 to the 5, tells us, again, there's no center of the expansion. We're looking at the radiation left over from the Big Bang, and that radiation doesn't in any particular direction. There's no center. There's no direction we can say, that's where the Big Bang was. The Big Bang was all around us and is now, 13.8 billion years later, all around us. And so logically and experimentally, there's no way of determining a center. And so we deduce that there is no center, because the space-time that we're a small part of was all originally one event.
Right, our next question is from Makluf, who is on with us live, who asked, why doesn't the sun burn all its hydrogen fuel within a small amount of time, a small moment? And why does it take millions of years?
That's a good question. I mean, why does the fusion rate is ferocious, and it's very hot, and the actual reaction rate seems very large, but the sun is also a large mass. So what is it that determines the lifetime of the sun? So the sun is, if the sun actually were denser and even hotter, it would burn at a faster rate and its lifetime would be shorter. So in any star, there's a trade-off between density, temperature, and fusion rate, or the rate at which you're burning the fuel. And in stars like the sun, these things balance out. There's an equilibrium reached where the pressure from the energy released in nuclear reactions balances the force of gravity and keeps the sun puffed up. In physics terms, this is hydrostatic equilibrium. So at every point within what we see as the sun, there's a balance between gravity in and radiation pressure from fusion out. And so that is what keeps the sun puffed up to the large size that it has. And that, in turn, is what keeps the reaction rate, or the rate of burning the fuel, fairly modest, such that the sun will take a total of 9 or 10 billion years to work through all its fuel. There's another aspect of this, which is that the sun is only hot enough in the central quarter, in terms of quarter of its radius, times turned into a volume. So that's about a 64th, or 2%, 1 or 2% of its volume. All the fusion is happening in that 1 or 2% of the volume, because that's the only part of the sun that's hot enough to cause nuclear reaction. So it's another part of the answer to the question, because the sun is not converting all its fuel all over the place and throughout its volume, but just in a very small fraction of its volume. Now, and you might then turn the question around and say, well, why doesn't it take forever for the sun to fuse? Maybe it should take forever because it seems so inefficient. And it is fairly inefficient. But the sun also has circulation, it has convection, just like a boiling pot of water. There'll be convection cells where the hot water at the bottom of the pan rises and then circulates. So the sun's plasma is circulating. And this mixing is what continues to take pure hydrogen from the outer parts of the sun towards the fusion regions where it can be turned into helium. So the sun has this sort of mixing or stirring going on, occurring naturally by convection, that helps it be a little more efficient. But even so, at the end of the sun's life, it will not have converted all its hydrogen into helium before it dies. It will be a somewhat inefficient process at the end.
Right, next question is from David, who's on with us live, who asks, on the subject of sending landers to search for life, how sterile can they actually be? Are we sure not even one microbe hitches a ride and causes contamination?
And that's a good question, and NASA worries about this quite a lot. I mean, NASA has always worried about contamination, but they take it very seriously now. I mean, there are two forms of contamination. There's, of course, the contamination of looking for life, say, on Mars, and worrying that you might be bringing terrestrial life there. And so, you're seeding the planet with the things you're looking for. Then there's the back contamination issue, which is if you bring back a sample or a spacecraft from the Martian surface and Mars has life on it, what if you bring those microbes back to the Earth? That's a scary prospect for some people. So Mars takes, NASA and other agencies planning to do this take these issues quite seriously. And NASA has pretty much committed in the last 5 or 6 years to not contaminate Mars and to clean up after itself. The simplest way that the contamination is dealt with is twofold, really. It's dealt with on Earth before launch. So space missions go through a sort of vacuum chamber sterilization and decontamination regime before they're made flight ready. But of course, they're not in a vacuum on the launch pad, and so you can quite reasonably guess that microbes could attach themselves to the outer part of the spacecraft or perhaps somehow penetrate into the inner regions of the spacecraft before launch. So the second place where the decontamination is executed is in entry. The Martian atmosphere is thin, but a large amount of heat is generated when a spacecraft enters Mars. And not all of that is absorbed and taken up by the heat shield. The whole spacecraft becomes very hot. And so that kind of decontamination is also undertaken. Now, does that guarantee that no microbe could ever hitch a ride to Mars and be present on the surface when we're looking for life, or going in the reverse direction? No, probably it doesn't. But it means the Martian surface is also quite sterile because cosmic rays and UV radiation come in through that thin atmosphere. So there's also a steady decontamination that happens just by natural sterilizing radiation as a probe sits on the surface of Mars. If we look for microbes, we're going to be looking for them under the surface, and so we'll need a pristine sample from under the surface.
All right, next question is from a live viewer who asks, when do you believe it is realistic that we will be able to send a manned mission to Mars?
Well, NASA's backed off quite a lot. So the American Space Agency has a plan to go to Mars, and that's been in place for more than a decade. But the current staged approach, which involves just robotic missions in the short term, 4, 5, 6, 7 years, sample return 10, 15 years, preparation for a manned landing 15 or 20 years, is in other words putting supplies there so that they can stay a significant amount of time. We're not talking about a Mars base, we're just talking about people in Mars for a period of time. So we're talking 20 to 25 years before NASA thinks they'll do it. There's no real other space agency that might do it on a quicker time scale. The Russians are too poor, the Chinese have interest, but they're still building their capacity, and the Europeans, it's not their priority. They're doing unmanned missions. So the only competition, of course, is the private sector. Elon Musk has made very aggressive plans for Mars, but even he's backed off some of his most bold claims, which involved getting the first colonists to Mars by the end of the 2020s, so maybe 10 years from now. most people think 15 to 18 years is a plausible time for people living even for a short period of time on the Martian surface. So the private sector may get there a few years ahead of NASA. That's always assuming NASA still has the money to do it. At least the private sector, if it's the commitment of a billionaire like Elon Musk and their company stays profitable, fueled by Tesla, of course, he hopes, then that's the timescale we should think of.
All right. We have 4 minutes left. We have time for one more question. This question is from Abhinash, who's on with us live, who asks, why do we look for water for the possibility of life on other planets? Maybe there are lives on other planets that don't need water to survive.
Absolutely. It's an assumption, and we just do it because life on Earth, all life on Earth is based on water or needs water, even when it has other ingredients. But yes, astrobiologists are quite aware that there could be other bases for life. So life essentially needs a liquid medium, that's assumed. It needs a solvent that can dissolve chemicals and cause interactions to happen and complexity to build for life to get started. And is water the only liquid that can do that? Absolutely not. There's a whole set of liquids that could possibly do it, from things that we consider quite toxic, like acetylene, to glycol, to the ethane-methane mixture on Titan. That's a very plausible alternate medium for life. It has a little liquid water mixed in and a little ammonia, but that's probably the most bizarre liquid people seriously consider might host biology. So it's a good question, and astrobiologists, when they're thinking broadly, absolutely understand there may be other bases for life than water. However, water is one of the most abundant molecules in the universe, so it's still a pretty plausible medium for life elsewhere. And thanks very much for your great questions this week, and we'll be back in a couple of weeks.